The machine is based on a standard vacuum chamber with a single door with a viewing port. There is a safety sensor on the top of the door that prevents the machine running when the door is open. To open the door, lift the two handles to disengage the locks. It is important when fitting components inside the chamber to wear gloves to keep surfaces as clean as possible. The test spindle, which is in the form of a standard rotary feed-through, is fitted to the top of the chamber. Different hubs can be fitted to the spindle for different test configurations. There are a couple of ports on the feed-through for optional water cooling. These ports are connected to a manifold on the back of the machine. The feed-through is driven by a servo motor. There is an earth cable which forms part of the electrical contact resistance circuit. A turbomolecular pump with a cooling fan is fitted on the right hand side of the chamber. The pump has ports for water cooling connected to the manifold on the back of the machine. Inside the chamber there is a mesh to protect the pump from ingestion of debris. The pump is connected by a stainless steel hose to a roughing pump. The vacuum system is controlled by a unit mounted on the back of the pump, which is controlled by the PC. At the bottom of the chamber there is a torque reaction mounted hub assembly which carries the lower specimen tooling mounted on top of the loading shaft. This is free to move on the vertical axis. The shaft acts through stainless steel bellows which provide the necessary leak-free sealing. The rotary feed-through and the loading shaft have been carefully aligned during manufacture and no adjustment should be made to the levelling screws. A flexural bearing resists rotation of the hub when torque is applied, and a capacitance sensor measures the displacement, which is proportional to the applied torque. On the back of the chamber there are electrical feed-throughs to provide the necessary connections. There are also halogen bakeout lamps. There are 3 thermocouple sockets at the back of the chamber. Socket 1 is for the lower specimen temperature. Socket 2 is spare. Socket 3 is for the washer thermocouple fitted to the back of the chamber for measuring bakeout temperature. A brown wire with a crimp ring is used to connect the lower specimen tooling to complete the electrical contact resistance circuit. A 3-way ceramic block is used for connecting the lower specimen heaters. The bottom of the loading shaft is connected to the machine crossbeam, which is loaded vertically by a servo-controlled pneumatic bellows. Column clamps have been fitted on the pillars to restrict the travel of the crossbeam. This is to prevent damage to the stainless steel bellows. A force transducer fitted to the pneumatic bellows measures the load and provides feedback for control. The force transducer is connected to a signal box under the machine with a potentiometer to zero the load. A switch on the front of the signal box is used to enable and disable the loading system. When the load system is active, the switch is illuminated. If the switch is then pressed, the load system is disabled and the light is turned off. A pressure switch is fitted to the air supply for the loading system. If the pressure is too low, the switch is triggered, an indicator is illuminated, and the loading system is disabled. The instrument cabinet has a green mains indicator light, a blue reset switch, and an emergency stop button. There is a duplicate emergency stop button on a flying lead, which can be placed next to the PC for easy access. The torque sensor is connected to the instrument cabinet amplifier. Pressing the reset switch activates the machine. The power module is fitted inside the frame on the left-hand side. The machine is switched on using the mains isolator on the power module. The door is also fitted with a green mains power indicator and a blue machine reset indicator. Before opening the chamber door, confirm that the vacuum system is switched off and that the chamber has vented back to atmospheric pressure. Lift the two handles to disengage the locks. If there is no vacuum, the handles will lift freely. If the chamber is still under vacuum, they will not. Do not try to force them. Opening the door activates the safety switch, disabling the motor, the load actuator, and the heaters. The load override button light will turn off, and once the bellows air has been vented, the cross slide will lower. Each test configuration uses a different upper specimen hub. 4-ball, pin on disc, and thrust washer. Hubs are secured to the spindle flange with 3 bolts. Start by attaching the 4-ball upper specimen hub to the spindle flange. Fit the heater pad on top of the torque measuring assembly. Connect the heaters to the screw terminal on the back of the chamber. Connect the contact potential lead to the heater block. Put a ball in the chuck nut and screw it by hand onto the chuck boss. Tighten using a spanner and a C-spanner. Put the lower ball cup on the locating dowels on the machine base and insert balls and clamping ring in the normal way. Tighten the locking nut with the box spanner. Do not over tighten. Add test oil or grease as required. Mount the ball cup on the heater pad and ensure that the assembly sits flat on the pad. Connect the thermocouple lead to the thermocouple socket 1. Now the machine is ready to run a 4-ball test. Start by fitting a disc specimen to the upper specimen hub with 3 countersunk screws. Next, attach the upper specimen hub to the spindle flange with the 3 bolts. Pin specimens are fitted in a mounting plate and held in place with grub screws. These hold the pins in place during handling and are not intended to take the applied load, so the pins must be long enough to go to the bottom of the holes. Place the plate on a flat surface and then insert and clamp the pins. Secure the mounting plate to the lower specimen base with 3 countersunk screws. Mount the base on the torque measuring assembly. Connect the heaters to the terminal block at the back of the chamber and secure the contact potential cable to the side of the base. Connect the thermocouple to socket 1. Make sure the tip of the thermocouple is pressed against the side of the pin mounting plate. If lubricated tests are to be formed, fit the fluid bath tube wall and add lubricant as required. The machine is now ready to run a pin-on-disc test. The upper specimen assembly is in two parts: a hub adapter that connects to the spindle flange and a specimen carrier disc. The hub and the disc are loosely connected by 3 shoulder screws, which allow the specimen disc to self-align with the lower specimen. Fit a thrust washer specimen to the upper specimen holder using an external circlip. Next, attach the assembly to the spindle flange with the 3 bolts. Fit the lower specimen holder onto the specimen base and secure using 3 cap head screws. Fit the lower counterface ring in the recess in the holder, engaging the anti-rotation pin. Mount the base on the torque measuring assembly. Connect the heaters to the terminal block at the back of the chamber. Secure the contact potential cable to the side of the base. Finally, connect the thermocouple to socket 1 and make sure the tip of the thermocouple is pressed against the counterface ring. If lubricated tests are to be performed, fit the fluid bath tube wall and add lubricant as required. The machine is now ready to run a thrust washer test. Note that it is possible to change both the thrust washer specimen and the counterface ring in situ. However, care must be taken to avoid contaminating the chamber if you do this. Before closing the door, check that there is no debris on the O-ring. Close the door by pushing on the 2 handles to engage the locks. Note that from time to time the O-ring may need to be greased with vacuum rated grease to enhance sealing performance. After tests, specimens and assemblies are simply removed in reverse order. Double-clicking the Compend icon on the Windows screen launches the software at page 1, the primary user interface screen. A single screen or page contains up to 40 boxes, and there are a total of 6 pages. Page 2 is for manual control of the high-speed data acquisition channels. Pages 3 and 4 are available for controlling additional peripheral devices if required and for additional sensors and derived channels. Page 5 is used for calibration. Page 6 duplicates boxes from page 1 and is used to define the order of columns in data files. It may also contain machine status information that can be used for fault finding. The current page number is shown in the top right-hand corner. The page displayed may be changed with a right or left click of the mouse or by pressing the page up or down key on the keyboard. Clicking on the File menu and selecting Show Setup displays the current setup and calibration files. The software version number and the configuration file loaded are displayed at the top left-hand side of the screen. In this case, the configuration file is for a T91 machine. There are a number of green boxes on the status bar. These indicate peripheral systems under the supervisory control of the Compen software. For a T91 machine, there are 4 peripheral components. The slim box refers to the Serial Link Interface module, which provides a microcontroller-based distributed control and data acquisition interface between the front-end software and the machine. A green box indicates that two-way communications has been established between the PC and the interface. At startup, or when a different configuration file is loaded, the slim box will temporarily turn blue while the software configuration is downloading from the PC to the microcontroller. It will revert to green once the software has been successfully downloaded. The box marked drive indicates communication between the PC and the motor servo drive, which is under direct digital control. The box marked TC400 indicates communications between the PC and the vacuum system controller. The box marked HSD indicates communication between the PC and the high-speed data acquisition card. The digital boxes on the screen are all color-coded to indicate function. Red boxes indicate outputs to the machine, including switches and set points, and with a few exceptions will have up and down toggle switches. Green boxes are inputs from machine sensors. Blue boxes are calculated channels derived from a number of sensor inputs. If a peripheral device box on the status bar turns from green to white, this indicates a loss of two-way software communications between the front end and the device. If the box turns red, this indicates a hardware fault with the comms port or the associated interconnecting cables. All peripheral device boxes must be green for satisfactory operation of the machine. Once the software has loaded, pressing the blue reset switch on the instrument panel enables the load actuator, provided the chamber door is closed and the machine air supply is turned on. The corresponding box on the screen changes from disabled to enabled. We can now run the machine under manual control. To apply a load, use the up and down arrows on the side of the red load set point box to adjust the load to the required value. Alternatively, you can double click on the set point box and insert a value using the keyboard. The resulting load, as measured by the loading system force transducer, will be displayed in the adjacent green load box. The value in the blue friction coefficient box is that derived from dividing the time-smoothed friction force signal by the measured load. The fixed specimen heater can now be enabled by clicking the up arrow on the red heater box. The temperature set point can now be set in just the same way as the load set point, using either the up and down arrows or by double clicking on the box and entering a value with the keyboard. The temperature as sensed by the thermocouple in the side of the specimen bath will be displayed in the green specimen temperature box. Note that large step changes in temperature set point are likely to cause the bath temperature to overshoot the set point. So under manual control, use small set point increments when adjusting the temperature. This issue is avoided with automatically controlled tests, where it is recommended that ramped set point changes are used. To operate the vacuum system, navigate to the page 3 screen to access the relevant control functions. The on-off switches send requests to the vacuum controller, and the enable-disable boxes display the corresponding response. 4 software functions are available. Roughing pump. This starts and stops the roughing pump. There will normally be no delay between switching on the pump and the response indicating that the pump has been enabled. Turbo pump. This starts and stops the turbomolecular pump. The pump will start without delay. However, some safety features are enabled to prevent damage to the pump, including stopping the pump after 8 minutes running time if the rotor speed is below 48,000 RPM, and stopping the pump if the temperature, or the rotor, the flange or the electronics, exceeds permissible values. If an error condition is triggered, the response on the screen will appear as disabled. An error code will be displayed in the turbo pump error box. Refer to the Pfeiffer vacuum documentation for a description of possible error codes. Vent admits air into the chamber via the intermediate stage of the turbomolecular pump. The solenoid valve will not open until the pump has slowed to below 30,000 RPM. Hence, there may be a delay between switching the valve to open and the response indicating that venting is enabled. Bakeout activates the halogen lamps in the chamber to raise the temperature of the internal surfaces to a preset maximum level. The default value is 80 centigrade. This aids desorption of volatile materials and is a necessary precondition for achieving ultra-high vacuum. Heating will not activate if the turbomolecular pump rotor speed is below 48,000 RPM. The motor can now be enabled by clicking the up arrow on the red motor box. The speed set point box can now be used to set the speed in just the same way as the other set points. The measured speed is displayed in the green speed box and the number of cycles in the green total cycles box. The count can be reset to 0 by pressing the up arrow on the red revolutions box. This is a momentary action switch and the display will revert to count after a few seconds. The final box to note on this screen is the green contact potential box, which displays a time-smoothed output from a Lum-Fury electrical contact resistance measurement circuit. Further details of this measurement technique and interpretation of the results are given in the manual. To record data while running under manual control, click on Data File on the toolbar and select Open Immediate Data File from the drop-down menu. This will open the Compend immediate data file directory. Either choose the name of an existing file to be overwritten or appended, or name a new file, then click Open. A drop-down menu will appear from which to select a data rate. 3 new boxes will appear on the status bar. The first of these will display the number of lines of data recorded. The third box shows the selected data rate. Click on the green Start box to start recording data. The box changes to a red box marked Stop. The data lines box value now increases as each line of data is added. To change the data rate while recording, click on the data rate box and select a new rate from the menu. To pause recording data, press Stop. To restart recording, press Start. To stop recording and close the data file, press Stop, then click on Data File on the toolbar and select Close Immediate Data File from the drop-down menu. To view the data file, from the same menu, select View Data File in Excel. Select the chosen file and click Open. The data file will now be displayed in Excel. The data is time-stamped and the order of the data columns follows the order of the boxes displayed on the screen page 6, reading top to bottom and from left to right. All boxes marked with a green square in the bottom left-hand corner will appear in the data file. To open an auto-scaling real-time graph, select Graph on the toolbar and Create Graph from the menu. The channels currently displayed are shown in the panel on the right-hand side. To edit the channel selection and change scales, click on Edit followed by Edit Graph Connections. This opens a new panel. To change the scale of a channel, select the channel from the list and edit the minimum and maximum values as required. Click OK to accept the change. In this example, we have changed the friction force range from 0 to 100 to 0 to 10. To remove a channel, return to the graph panel, select the channel to be removed, click Disconnect, followed by OK. To restart the graph, select Graph on the toolbar and Reset Graph from the menu. To add a new channel, return to the graph panel, select an unused graph connection in the left-hand window. The right-hand window lists all available channels. Select the channel you want and click Connect. Next, set a minimum and maximum value and click OK. The new channel is now added to the list of channels displayed and the trace appears on the graph. The graph is auto-scaling, so the trace is progressively compressed, with the 0 on the time axis, the time when the graph was last started. This allows the operator to view the entire test from that time to the current moment. To close the graph, click on File on the graph toolbar and select Close Graph. High-speed data acquisition can either be triggered manually or automatically programmed within a test sequence file. Manual controls are on screen page 2. The sampling rate and sample size can be set in the boxes provided, and the sampling executed by clicking on the up arrow in the HSD trigger box. This will sample all the inputs physically connected to the high-speed data acquisition interface. The sampled data is displayed in a new graph window. Note that this is overwritten every time that high-speed data is triggered. The window can be repositioned on the screen as required. In much the same way as the low-speed data graph, the high-speed graph can be rescaled by clicking on Edit and amending the values in the table presented. The associated data file can be accessed from the C-Compendex data directory and is called DTHSD. In the case of the TU91, there are three inputs connected to the high-speed data acquisition interface: speed, torque, and load. Note that this file will be overwritten the next time manually triggered high-speed data is triggered. So if you want to keep the data, save the file under a new name. Clicking on Test Sequence on the toolbar presents a menu allowing the user either to create a new 10 or 20-step test sequence file, or alternatively to open an existing test sequence file. Selecting an existing file and clicking Open generates two new windows. The upper window is Control, which is used to start and stop the test, and also to create a data file. The lower window is Test Sequence, which is used to view and edit the test sequence file. This window can be maximized either by clicking on the Maximize button or by double-clicking on the title bar. The control panel can now be minimized by using the Minimize button. Selecting File on the toolbar and Save from the drop-down menu will save the file. Selecting Save As will allow the file to be saved under a new name. The file name is shown at the top of the spreadsheet. Selecting View on the toolbar, followed by Reveal Comment column from the menu, will add a column for adding notes about the test. The next column is Step Number, which is the logical order of steps, but not necessarily the sequence in which they are executed. This column is followed by the Next Step, which defines the step-to-step sequence, hence the actual sequence of steps in the test. This column includes the facility to include loops and calls to subroutines. Right-clicking on the Next Step box will open the parameter window for the current step. In this case, if I click on the Next Step box for step number 1, the parameter window shows Go to Step 2, which is the next logical step, and is entered automatically when the Next Step button is clicked. I can, however, manually enter a different Go to step, should I wish, thus creating a jump. The parameter box also includes facilities for program variable conditions, for executing a step, and for setting a loop count, which appears in the next column. We will cover this later in the presentation. The fourth column is step time in seconds. This can also be used to pause the test, for example, so that the operator can perform a manual task as part of the sequence, or to program conditional steps or jumps. Once again, this will be covered in detail later. Clicking on the step time box opens a parameter window. In this case, the selected step time is 2 seconds. The data mode column shows the data rate programmed for a given step. Clicking on the box opens a parameter box. The maximum data rate for low-speed data is once every 0.1 seconds, in other words, 10 Hz sampling rate. There is also the facility to program opening of a new data file during a test. Data files cannot be viewed when they are being written to, so if you are running a very long test and want to view blocks of data while the test is still running, opening a new data file and closing the previous file will allow the latter to be opened and viewed. The next columns all refer to control parameters corresponding to all the red box items on the main page 1 screen, including switches and set points. There are also columns for programming high-speed data acquisition, in other words, the red box functions on the page 2 screen. In this example, a test to ASTM D2266, the first step is used to set up some starting parameters before set point control devices are enabled. The temperature set point has been set to 20°C so that when the heaters are enabled, there is not a large difference between the set point and the ambient temperature. It's also sensible to do such things as including a reset of the cycle counter. Finally, it's sensible to set the speed set point to 0 rather than a positive value, so that motion does not start instantly as soon as the motor is enabled. In step 2, a load of 392 newtons is applied. You will see that the value 0R appears in many set point columns. This stands for zero relative. For example, the temperature set point for step 2 is given as 20°C. Right-clicking on the value will open a parameter box in which the value can be set to 0R. This means that there is no change relative to the set point in the previous step. So in this case, the temperature set point will remain at 20°C. The set point parameter box allows the user to switch between a relative value and an absolute value. In the third step, both the roughing pump and the turbomolecular pump are enabled. The step time is set to 3,600 seconds. As well as programming a fixed time, the step time can also be programmed as a conditional step using the associated parameter box. There are a number of conditions that can be selected. Right-click on the step time box. In this case, I'm choosing step when less than or equal to. Select an option and a browse list of parameters is presented. In this case, I have chosen chamber pressure from the list and entered a trigger value of 1 nanobar in the yellow box. The step time box now shows C step minus, indicating a falling value conditional step has been programmed. The test will now move to the next step once the chamber pressure falls below 1 nanobar. In step 4, the heater is enabled and a temperature set point of 75°C is programmed, with a ramp time of 1200 seconds, thus ramping the temperature set point from 20°C to 75°C at a rate of 2.5 C per minute. The transition to the next step is another conditional step and has been set when the temperature is greater than or equal to 75°C. In step 5, the motor is enabled and the motor speed set point has been set to 1200 RPM with a ramp time of 10 seconds. The test will run for the required amount of time, in this case 3600 seconds. Don't forget to have a data mode set if you want to record any data. In this case, the data rate is set to collect data every 10 seconds. At step 6, the motor is stopped, and at step 7, the test load is removed. Finally, in step 8, the vacuum chamber is vented with a conditional step on chamber pressure, with the test terminated when atmospheric pressure is achieved. This step includes the exit statement as the next step. This defines the end of the program and closes the test. If you wish to run a test unsupervised, it is sensible to set alarms in the test sequence file. Click on Alarms on the toolbar. This allows the user to program high and low level warning and shutdown alarms on all analog, pulse counting and derived channels on a step-by-step basis. It is important to note that when a new test is created, no alarms are set. When creating a new test, it is important to set alarms suitable for the test parameters, or as an absolute minimum, use the Set All Steps to Default option to ensure that the test parameters do not exceed the machine's capabilities. Alarms may be set for each step in the test and for each required parameter, although it is usually only necessary to set alarms on the most important parameters, for example, load, temperature and friction. Use the up and down arrows next to the step number box to pick each step. Then set the alarm levels for the required channel from the list on the right. The alarm levels may be copied from one step to another using the Copy Step and Paste buttons. When an alarm is triggered, a message will appear above the control panel and the event will be recorded in the data file. A shutdown alarm will terminate the test. If you have modified the test sequence file, save the changes, then click the Minimize button to revert to the comp end screen. To restore the control panel, click on the comp end icon on the bottom toolbar and select the item from the menu. If windows have been resized and moved on screen, the default layout can be restored by clicking Arrange on the toolbar. To run a test, start by clicking Data File on the control panel. Then select Open Data File from the menu. The comp end data file directory will open. Either select an existing file to be overwritten or appended, or create a new data file by entering a new name, then click Open. The data file name appears in the control panel box. Having checked that the machine is ready to run, press Start. If you have not previously saved your test sequence file, a prompt will appear. Next, a panel will appear to allow the operator to enter details of the test to be performed. This information will appear at the top of the data file. Once this has been completed, the test will start. When the test has ended, as with the manual test, click on Data File on the toolbar and select View Data File in Excel from the menu. The test sequence file allows loops to be programmed. When used in conjunction with a relative set point, loops allow the user to program incremental steps. In this example, I'm programming a loop to increase the load set point from the current 100 newtons in 100 newton increments up to 500 newtons. To do this, I start by inserting a new step in the sequence. Select the step which is to follow the new step, click on Edit on the toolbar and select Insert New Step. The necessary notes can be added in the comment column and all the subsequent control parameters set, including setting the load set point to 100 newtons relative. A value 100R now appears in the load set point box for the next step. We have to make sure that all the other set points are correctly entered for this new step. Finally, we have to set the appropriate next step value and loop count. In this example, our new step is step 5. So to create the loop, we must set step 4 as the next step. If we now enter a loop count of 4, the test sequence will execute step 4 at the 100 newton load set in step 3, then increase the load by 100 newtons relative to the previous value in step 4. Hence, the first loop increases the step 4 load to 200 newtons, the second loop to 300 newtons, the third to 400 newtons, and the fourth and final loop to 500 newtons. On completion of the required number of loops, step 5 will move on to the next logical step, which in this case is step 6. With the load increasing each time the loop is executed, it is important to set the alarms for the steps within the loop to values appropriate for the maximum set point value achieved during the loops. If we now run the test, we can observe what happens on the real-time graph. We will, of course, have to rescale the graph to accommodate the changed test parameters. To program high-speed data acquisition within a test sequence file, click on the HSD sampling rate box and enter a value. In this example, I'm setting the sampling frequency to 5 kHz. Next, click on HSD samples and enter the number of data lines to be collected. In this example, I have set 5,000 data lines, which means that with a sampling rate of 5 kHz, 1 second of high-speed data will be recorded. Note that the ramp time is not a relevant parameter for high-speed data acquisition. The next column sets the data acquisition mode, further details of which can be found in the manual. The most widely used mode is Mode 1, Internally Pace. This uses the internal clock on the high-speed interface as the trigger. Having set the required high-speed data acquisition parameters, entering 0 relative in subsequent steps will keep the parameters unchanged for those steps. To trigger high-speed data acquisition at various points in the test, we can program a loop. We start by adding a step during which high-speed data acquisition is triggered. In this example, I will amend step 4 to run for 170 seconds with the new step, step 5, during which high-speed data acquisition will be triggered, lasting for 10 seconds. Step 5 then goes to step 4 and the loop count will be set to 9. Hence the step 4 and 5 sequence will be executed a total of 10 times, giving a total runtime of 1800 seconds as before. If we now run the test, we can see what happens. If we want to see the high-speed data while the test is running, click on Graph on the toolbar and select High-Speed Data Graph from the menu. The graph window can be repositioned as required. Every time high-speed data is triggered, the graph window will update. We can move between the high and low speed graphs if required by clicking on the graph icons. Every time high-speed data is generated, a new data file is created and an entry made at the relevant point in the low-speed data file. At the end of the test, we can open the low-speed data file and scroll down to each high-speed data file. Automatically generated hyperlinks are provided for accessing the high-speed files directly from the low-speed data. Alternatively, individual high-speed files can be opened in the Compendex data directory. You may want to run tests using a common test sequence, but with changes to a given control parameter. You could, of course, simply edit the test sequence file each time you wanted to change the parameter. Alternatively, the software allows the user to program a variable set point as opposed to a fixed value. The user is then prompted to enter the required value at the start of the test. To create variable set points, click on View on the Test Sequence File toolbar and select Variable Table from the menu. This generates a table for defining variable set points. In this example, I have defined test load, temperature, frequency and duration as variable set points. Now click on the required set point box, for example, load at step 3. Instead of using a set point of 100 newtons, as shown, click on the Use Variable box and select Load from the list of previously defined variables. The value in the box now appears as a set point of V1. We can now use the other variables as required, for example, V2 as the temperature set point for step 3. We can also use a variable for the value in a conditional step. So instead of using 80 degrees centigrade as shown here, we can choose variable V2 by selecting temperature from the list. Once we have defined all the required variables, we can save the test sequence file and run the test in the normal way. When Start is pressed, the previously defined variable table is displayed. The required values for this particular test are entered. When OK is pressed, the test starts as normal and runs with the set point values defined in the variable table. That concludes this instructional presentation. If you would like to access specific sections, please choose the appropriate place from the timeline.